Very pleased to introduce Emil Saucan, who I guess you're at the Royal College of Engineering. I had you listed somewhere else. Fantastic. Going to tell us been around a few places lately. I totally understand. It's anyway. We're glad to have you here. And he's going to tell us about geometric persistent homology for networks and hypernetworks.
Thank you so much for having me here. I would like to thank the organizer for the opportunity, giving me the opportunity of this talk. And I should say that I can't hardly notice that my talk is somehow different in scope from the other ones. But I thought that these networks are indeed discrete shapes, and also the methods I talk about are discrete curvatures, honest to God discrete curvatures. So I hope I wasn't too much mistaken in choosing this subject. So, so of course, as I said, I'm talking about discrete curvatures. And why can I say that? Because it's lately, people think of networks as as graphs, but lately people have started looking at them as higher dimensional objects. Why? Well, because you want to use more topology and geometry, and that's for one. On the other hand, you want to capture interactions, not just between pairs of nodes, but triples and so on and so forth, which are more expressive, yes, in biology and social sciences, and just to mention these cases. So there is more than one method of making a higher dimensional polyhedral complex out of a network or a hypernetwork. One, it's kind of common by now, is to build a clique complex. Plumbing in a triangle for every complete free graph, a pyramid for every complete foregraph, and so on and so forth. Many are doing it, Bianconi, for instance, and I'll make appeal to it at some point in the beginning. There is a more general way of looking at networks, the most general that I found, and we did introduce a polyhedral structure on it. And there is a canonical way of looking at them, going through using blocks work, just viewing them as posets and introducing plumbing against faces for every path of length to a triangle, for every path of length free tetrahedron, and so on and so forth. So there is more than one way, as I said, to do persistent. It's about persistent homology. So the first one makes appeal to Foreman's Morse theory, which is kind of popular. I just remind a few facts about it. In fact, it's so popular that I would need at least as much time as I have for the whole talk just to browse through all the applications. There are quite a bunch of very beautiful ones, and it's classical by now. So this is discrete. It's defined again on simplicial complexes. The Morse function, the height function, is not a continuous one, and you give a higher height to higher dimensional faces, maximum with one exception. So this is not a discrete Morse function, and this one is. But sorry, I can't get into details. It's a well-known method by now. And I'm sure people know it here. Most of, if not everybody, knows it much better than I do. And it captures all the essential topology, the homotopy and the homology of what you would expect from a Morse theory. And it's good in practice because you can construct these good discrete gradient vector fields, and they are quite practical. So what does this have to do with persistent homology? Well, we recently tried it to produce using, it's very natural to use Morse theory to do persistent homology, and that is kind of natural to use Foreman's Morse theory. So again, we used it on the clique complex, and it's good not just for because you can look at higher dimensional faces with natural for multiplex, I mean higher leveled networks and hypernetworks. It's very efficient because it achieves almost a theoretical minimum number of critical simplices as given by Forman's theory. And it produces a very efficient and reduced, in that sense, filtration scheme, because you just go through the critical phases, simplices if you prefer. So it's efficient. So because you introduce the higher order phases, then of course you can analyze your network in higher dimensions, so corresponding further relations. So the only problem is that it's Forman's Morse theory goes for unweighted graphs. It's a purely topological construct, and we need some ways to do the filtration. And so there is an algorithm kind of involved which does that, but it's possible. And then you get filtration. So there are a few results here. We produce them. We add phases according to weights, and observe there is a big stage here, but if you can see it into detail, there is a substage when you pass from this one to this one. This is being the order of things. And you can see the ubiquitous barcodes. That's why you do it, to get these barcodes. Okay, so that's what you can say about this Forman Morse theory. Another approach would be, so these friends of mine, Arijit Samal and Dravaroy, we discussed about it, and since we work already on the Forman curvature, this time not Morse theory, they said, well, let's try that also, and they did. And so I need to remind you, or to introduce at least the formulas for Forman curvature. This is a one-dimensional case which it's a degeneration of the proper formula for the one-dimensional case, and it's something which we tried with Jürgen Jost and Arijit Samal and Melanie Weber, and it works quite well. In any case, this goes for weighted networks, as you can see. So you can plumb in the weight of an edge, any edge, the weight of the nodes, and to obtain the Forman curvature of the red edge. So again, if you want to compare it, and given that most networks are given as combinatorial, we would like very much to introduce some weights. So there is a way of introducing weights. It's not theoretically very deep, but it works in practice, and you can see the filtration here and the associated barcodes. And of course, I can't, again, it's not I'm just doing an overview of the geometric approach to persistent homology for networks. So I can't go into details, but we tried and they tried for different types of networks, and there was some comparison done. So that you can do the comparison. You consider the bottleneck distance, the W infinity distance between barcodes, which is defined, of course, like this. And what you can see here is are the distances, the W infinity distances between the model networks and random spherical and hyperbolic networks. And again here, so what's the difference? This table is for the Forman Morse theory, and this is for Forman curvature. And so why am I giving both of them? Because my friends were kind of embarrassed that the results were looking too similar in places. So they thought perhaps somebody would think that they bluffed the results. And so Rava, who's a pure mathematician at heart, by education, he tried to explain it and he couldn't. So I think I do have an explanation. Sorry. So there is yet another most geometric and discrete Morse type of Morse theory. It's not Forman's, but it's far earlier, some 21 years before, was introduced by Branchoff for polyhedral manifolds. And I don't know how well I'm with time, with respect to time. And I think I prepared a bit too many slides about this one, but it's very geometric. It goes for polyhedral complexes in, let's say, in R3. So you have to introduce define an index. So if you have a direction L, then the index of the point P at relative to direction L is given by this formula. Only problem is that, so it coincides in the case of smooth manifolds, it coincides with the basic definition. If it's 0, it's a regular point, but what is a small circle? This is a kind of a problem. So it's not such a big problem because for polyhedral manifolds, actually small circles are stars of the vertices. So you can talk about general height functions, which are very naturally defined in this manner for different vertices will have different heights. And vertices can be either saddle points or minima or maxima, and regular points, I mean, points on edges and on faces are ordinary points. And so this is an example. This is after Branchoff. And in any case, what I would like to say that if you try this discrete index and you try to compute the Euler characteristic is the right one. At least that's something good. But it's kind of hard to follow this method of finding the index. So the simple method is to look at a vertex, to say it's a middle vertex, it's one of these neighbors is above this plane and the other one is below this plane. And the formula is very simple of the index. Should be L. It's 1 minus half of the number of triangles for which V is a middle vertex. So this is, I'm sorry if people who know this much better than me are bored, but since this is older than 4 months and it's less famous by now, so I thought I should bring it up here since I will be using it, of course. And again, you can obtain the Euler characteristic as the sum of the indices of the vertices. So of course, this holds in any dimension. So what can I say? So you have a proper Morse theory, you have the indices, you have these complexes in R3 or Rn for the matter. Therefore, you can produce, and moreover, hypernetworks, we just realized anymore, we can realize them in more than one manner as polyhedral complexes. Therefore, the result is that there exists a discrete curvature-based persistent homology scheme for hypernetworks. And when I say persistent discrete curvature, I mean discrete in the sense of defect, like in graphics, classical. I skipped a few facts that connect the index and the defect curvature, but they kind of obvious, so to say. Okay, so now this is something new. There was a problem. And moreover, so now we're in the very happy situation with two different discrete Morse theories for polyhedral complexes. One is of Formans and one is Branchoff, and they are very different. One is purely combinatorial. The other one is very intuitive. We published it, a paper in American Mathematical Monthly about that. So, and very geometric. So is there a connection between the two of them? And in fact, there is. There is this theorem of Bloch that they say that for finite regular CW complexes, they are basically the same. That means that you can realize your complex in a high enough Euclidean space, so such that Forman critical cells have barycenters which are Branchoff critical and the other way around. So it's kind of nice. So there is this translation from cells to vertices, but from barycenters, but that's okay, at least in theory. Moreover, it turns out that Forman discrete Morse theory is more accurate than even the smooth one in bounding the homology of a manifold. And on the other hand, for smooth manifolds, classical Morse theory and discrete Morse theory, I mean, Forman discrete Morse theory are equivalent. So even Branchoff theory are equivalent in dimension lesser than 7, which is much more than we use in practice for persistent homology anyhow. So therefore, if you combine these results, you can surmise that there is a persistent homology scheme which is efficient for hypernetworks, not just for networks, and not just by constructing these are somewhat arbitrarily cliques, simplexes, but in a natural way of defining hypernetworks. Okay, so what's good and what's bad? So Branchoff is far more geometric, more intuitive in dimension 3, harder to see in dimension 3. Forman Morse, it's less intuitive, but it's very simple to use on raw data. That's why people use it in computer science. But Forman Morse works only for unweighted hypernetworks, whereas in real life you have weights on vertices and edges. And moreover, you can metricize using these weights. You can metricize the network, hypernetwork, and obtain a polyhedral complex and apply Branchoff on that one. So it's a plus for Branchoff. So there are a few problems, at least 2 of them. So the problem is Branchoff Morse holds for PL manifolds and some more general convex cell complexes. So, and one might object that, well, if you realize a general network as a simplicial complex, let's say, it's not that nice, yes? Might be not a PL manifold. But then there is a way out of it. There is a generalization due to Bloch again, which is called a stratified Morse theory, which holds for this kind of object as well. So that's good. That's a positive one. On the other hand, the Branchoff Morse theory, as we said, even if theoretically it holds in dimension 17, say, it's not that easy to see or to implement it. And then there is a way out of it. The solution is to use the Forman-Ricci curvature. So that will be the connection between which I mentioned, between the results which my friends obtained, yes, and couldn't explain. So if you use a proper definition as per Forman of Forman-Ricci curvature, the Ricci, and you just look at triangle, let's say, then the Ricci-Forman curvature of an edge is given by this formula when this is the number of triangles in which the edge is included. So, and the U and V are the edges adjacent to E, the defining edges. So then you can define, of course, take the mean of all these Forman curvatures, sorry for the change of notation, and define the scalar curvature is just the sum of the curvatures of all the edges adjacent to V and dividing by the number of edges. So this is commonly done, and this is when people write a lot of papers on the Ricci curvature of this and Ricci curvature of that. They mean actually the scalar curvature because they look at vertices and not at edges as it would be proper for a Ricci curvature. And then I think my time is almost up, if I'm not mistaken, but that's why I'm rushing things a bit. My apologies. And there is a connection with the scalar Forman curvature of the vertex V and the defect curvature, the discrete curvature of the vertex V. So when you do Branchoff curvature, you look at the curvature of the discrete curvature, a combinatorial curvature, defect if you prefer. But that's essentially the same as using a scalar Forman curvature, which is much simpler to compute. It's very combinatorial and you don't have to compute angles. You can do it very easily in very abstract sense. So it's a plus, and this explains the results because all these versions of Forman curvature are very well correlated. So that's that. So we can just summarize by saying that there exists a Forman-Ricci curvature based persistent homology for hypernetworks. And that concludes my talk. And I'm sorry, I think I rushed it horribly, but I tried to present more than one trick. And the head was a bit too small to allow this rabbit. So thank you so much. And that's all. Thank you.
Thank you. Thank you. I think we have time for a question. Sure. Okay. Well, I was wondering, sort of. It sounds like there's certain applications that you've been working on with this. Maybe you could say a word or two about some places where these sort of curvature-based persistent homologies have been fruitful.
So for now, we are just beginning. So we discussed this, as I said, we discussed this very simple formal curvature combinatorial one, and there is that paper which analyzed. It's more a statistical analysis. It's a proof of capability, so to say. And we are working on a paper, again, using this posets approach. But unfortunately, I lack a student who can do the computations for. So I think it would be much more efficient in all cases when you need a geometric approach. So for applications as graphics and imaging, it would be even more stronger than all. I mean, it would be also more natural to use this, classical combinatorial curvature for persistent homology as opposed to, I don't know, Forman's Morse, which is kind of out of context there. My hope is that it would be good for, for persistent homology of more this kind of hypernetworks and more layered type of networks where there is very little done which is not proper machine learning, at least that I know. I don't know if I answered your question. I try to be honest about it anyhow.
No, it's good. It's good to know sort of where you're going and where those are.
Well, I am trying to do a bit of theory and to round things up, but of course, when opportunity arises, I will try to apply it to something like machine learning, for instance. Of course, if you have any suggestions, I would be glad to hear anyone.
Great. All right. Well, thank you again.
Thank you. Thank you. Thank you for having me. So I'll stop sharing my screen, yes?
Yeah, if you could stop sharing your screen, then we will get the next speaker up.